Hello, in this lecture we will answer on two questions. The first question is to find out the area of this semicircle that is inscribed inside the quarter circle, and the second question is to find out the size of this angle theta, that is one angle of the right triangle ABC, and we will answer on those two questions in two different methods. Okay, so we start with the first question. We will answer on this question in two different methods. So in the drawing we have a quarter circle and a semicircle that is inscribed inside the quarter circle. We know that the radius of the quarter circle is equal to 3 units, and we want to find out the area of this semicircle. So we will start with the first method. So here we will define the center of the semicircle at this point C, and from point C, that is the center of the semicircle, we will draw the radius of the semicircle, and we will define the radius of the semicircle as R. Here the radius of the semicircle, actually it is drawn to the point of tendency of this of the radius of the quarter circle. So this will be AB. AB is tangent to the semicircle at this point. This is the point of tendency. We define this point as point D, and we have the rule that rule number 1, that a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So this radius, it is drawn to the point of tendency, that is to say, it is drawn to the point D, that is the point of tendency of tangent AB with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then the tangent AB will be perpendicular to the radius DC. That is to say, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Likewise, from point C, that is the center of the semicircle, we'll draw the radius. This radius is drawn to the point of tendency. We define this point as point E, this point is point F, and this point is point G, and we will define this point as point H. So here the radius CH of the semicircle, it is drawn to the point of tendency, that is to say, it is drawn to point H, that is the point of tendency of tangent BE with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then the tangent BE will be perpendicular to the radius HC. So BE is perpendicular to HC. That is to say, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. And because of the fact that ABE is a quarter circle, this angle must be equal to 90 degrees. So actually, in quadrilateral DCBH, we have three right angles. In quadrilateral BCDH, we have 1, 2, 3 right angles. The sum of three right angles is 90 times 3 is 270 degrees, plus the size of the fourth angle, that is actually angle DCH, this the missing angle DCH. In total, the sum of those four angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. We'll subtract 270 degrees from this equation, and we'll get that the missing angle DCH, is equal to 360 degrees minus 270 degrees, it is 90 degrees. So we found out that the missing angle equals to 90 degrees, it is a right angle. So actually, quadrilateral DCBH is four right angles. Any quadrilateral that has four right angles must be at least a rectangle. Okay, any quadrilateral that has four right angles must be at least a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, DC equals to BH. DC equals to BH. But we know that this is the radius of the semicircle, that is to say it equals to R. From this equation, R equals to DC equals to BH, we will derive that BH is also equals to R. BH equals to R. Likewise, side CH of rectangle DCHB must be equal to DB according to the rule that the opposite sides of the rectangle are equal to each other. So CH equals to DB. But CH equals to R. CH equals to R. And from this equation, R equals to CH equals to DB, we derive that DB is also equals to R. DB is also equals to R. So because of the fact that all the sides of quadrilateral DCBH are equal to each other, they are all equal to R, it means that quadrilateral DCBH is a square. Okay? I'll write it down that quadrilateral DCBH is a square. We will draw the diagonal of this square. We will join points B and C together by a straight line. And BC is the diagonal of the square. So, in the right triangle BCH, according to the Pythagoras theorem, we get that BH squared plus CH squared equals to BC squared. In the right triangle BCH. According to the Pythagoras theorem, PT is the relation for Pythagoras theorem. We get that BH squared plus HC squared equals to the square of the hypotenuse, that is BC squared. Here BH equals to R, so BH squared is R squared plus HC squared. HC is also R, so HC squared will be equal to R squared, that is okay. So HC equals to R squared, HC squared equals to R squared, and it equals to BC squared. BC squared. So R squared plus R squared is 2R squared, and 2R squared equals to BC squared. Here we take a root out of this equation, and we get that the size of the diagonal BC of the square is equal to square root of 2 times R. So here we can write down that the size of BC equals to square root of 2 times R. Here we will extend the diagonal BC until it touches the quarter circle. We will define the touching point of the extended BC with the quarter circle as point S. So what is the size of the line segment SC? SC will be equal, actually BS is the radius of the quarter circle, that is 3 units. 3 units minus the diagonal BC is the value of CS. So it is 3 minus the length of the diagonal BC, that is square root of 2R. So in conclusion, we found out that line segment CS equals to 3 minus square root of 2R. In the next step, we will do a construction. We will complete the quarter circle to a circle. So we completed the quarter circle to a circle, and in the next step we will extend line segment BS until it touches the circle, and we will define the touching point of the extended line segment SB with the circle as point M. MB is the radius of the quarter circle, that is to say it is equal to 3 units. Okay? And we actually have a new rule. When you have two chords that intersect with each other inside a circle, I repeat again, when two chords intersect with each other inside a circle, here we have this circle. Inside this circle we have two chords that intersect with each other. This is chord AB. Chord AB intersects with chord CD. We define the intersection point as point O. Again, point O is the intersection point with chord A. With point O is the intersection point of chord AB with chord CD. Here we have the following equation is true. Here AO times OB is equal to CO times OD. Okay, so whenever you have two chords that intersect with each other inside the circle, then the following equation is true, that AO times OB equals to CO times OD. We will implement this rule in our drawing. In our drawing we have chord MS. This chord MS that intersects chord MS intersects with chord GF at point C. Point C is the intersection point. So according to the rule that I presented to you, we'll get that the following formula is true, that MC times CS MC times CS is equal, MC times CS equals to GC times CF. Okay, chord MS intersects with chord GF inside this big circle. Therefore, according to the rule that I mentioned, MC times CS equals to GC times CF. GC, it is very easy to see that GC is the radius of the semicircle, that is to say it equals to R, and CF is also the radius of the semicircle, that is to say it is also equals to R. So we'll put the values of those line segments inside this equation. We'll get that MC equals to 3 plus square root of 2R, 3 plus square root of 2R, CS equals to 3 minus square root of 2R, and it is equal to GC, that is R, times CS, that is also R. In conclusion, we found out that 3 times square root of R times 3 minus square root, 3 plus square root of 2R times 3 minus square root of 2R equals to R times R. And according to the formula that A plus B times A minus B equals to A squared times B squared, here A equals to 3 and B equals to square root of 2R, so A squared will be equal to 3 squared, that is 9, minus B squared. B is square root of 2R. So square root of 2 is 2, and the square root of R is R squared. So in conclusion, it is 2r squared. So this side of the equation equals to 9 minus 2r squared, and r times r is r. So in conclusion, we found out that 9 minus 2r squared equals to r squared. Here we will add 2r squared to this equation, and we get that 9 equals to 2r squared plus r squared is 3r squared. Here we will divide this equation by 3, and we get that 9 over 3 is 3. 3 equals to r squared. We found out that r squared equals to 3, and the area of the semicircle is equal to the area of the circle equals to pi r squared, and the area of the semicircle will be equal to half of it. That is to say, the area of the semicircle will be equal to pi r squared over 2. Pi r squared over 2. So it is equal to pi. R squared is 3. We found out that r squared equals to 3. So r squared is 3 over 2. So in conclusion, we found out that the area of the semicircle is equal to 3 pi over 2 square units. We finished with the first method. In the next step, I will present to you how to find out the area of the semicircle according to the second method. Okay? We will use the things that we found in the first method in the second method. So, in the second method, we have already found out that we have here if this is the center of the semicircle, that is point C, then we already found out that we have here a square. So it's A, B, C. So BC, ABC, quadrilateral BCED is a square. That is what we have already found out in the first method. Here, this is point F, this is point G. We will join points E and F together by a straight line. It is very easy to see from the drawing that EF is the radius of the quarter circle. That is to say, it is equal to 3 units. And we will also join together points G and E by a straight line. It is also very easy to see that EG is also the radius of the quarter circle, that is to say it equals to 3 units. And we have already found out that CF is the radius of the semicircle, that is to say it is equal to R. CG is also the radius of the semicircle, that is equal to R. This is the diagonal of the square. We have already found out that the diagonal of the square equals to the square root of 2R. Actually, we have in isosceles triangle. Why? Because triangle FEG, triangle FEG is an isosceles triangle. Here, the green triangle, triangle EGF is an isosceles triangle. And we have another rule, and actually EC is the median to the base. EC is the median to the base that bisects the base. EC bisects the base to two equal parts. That is to say, this EC equals to R and CG is also equals to R. So the median EC to the base FG in the green isosceles triangle, triangle FEG, bisects the base. But we have also rule about the median to the base in an isosceles triangle. According to the rule number 1, the median to the base in an isosceles triangle is perpendicular to the base. So I read rule number 1 again. According to rule number 1, the median to the base in an isosceles triangle is perpendicular to the base. So we have already found out that triangle GEF is an isosceles triangle because of the fact that FE equals to EG equals to 3 units. It is the radius of the quarter circle. And we also found out that EC is the median to the base. Why EC is the median to the base? Because it bisects the base to two equal parts. This part equals to R and this part is also equals to R. And according to rule number 1 that I mentioned just right now, the median is not only bisects the base, but it is also in an isosceles triangle. The median to the base is not only bisects the base, but it is also perpendicular to the base. That is to say, EC is perpendicular to EG. If EC is perpendicular to EG, it means that this angle is equal to 90 degrees and this angle will be also equal to 90 degrees. So if we focus on the right triangle, triangle ECF, I will copy the right triangle, triangle ECF in a new page. know that EC is the diagonal of the square that is square root of 2r. We know that FE is the radius of the quarter circle, that is to say it is equal to 3 units. And we know that FC is the radius of the semicircle, that is to say it is equal to r. And according to rule number 1, this angle is a right angle, because of the fact that the median EC bisects, it is also perpendicular to the base FG. So we have here a right triangle FCE is a right triangle, and we will implement the Pythagoras theorem on the right triangle FCE. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, the hypotenuse is FE, the square of the hypotenuse is FE squared, and it is equal to the sum of the squares of the perpendiculars. That is to say, it is equal to FC squared plus EC squared. FC is 3, so FC squared is 3 squared, that is 9. FE is 3, so FE squared is 3 squared, that is 9. FC is R, so FC squared is R squared plus EC squared. EC is square root of 2R, so EC squared will be equal to the square root of 2R squared, that is actually 2R squared. So we found out that 9 equals to R squared plus 2R squared. R squared plus 2R squared is 3R squared. So we got that 9 equals to 3R squared. We'll divide this equation by 3, and we get that R squared equals to 3. R squared equals to 3, and the area of the semicircle is equal to pi r squared over 2. Okay, pi r squared over 2. Pi r squared is 3 over 2. So we found out that the area of the semicircle, it is equals to 3 pi over 2 square units. Okay, so we finished with the second method. In the next step, I will present to you the second question. In the drawing, we have a right triangle. Triangle ABC is the right triangle because of the fact that angle ABC equals to 90 degrees. We also know that line segment DE is perpendicular to AC. That is to say, this angle equals to 90 degrees, and this angle is also equals to 90 degrees. And we know that AE is equal to EC. We also know that BC is equal to 6 units, and we know that DE is equal to 2 units, and we want to find out the size of this angle BAC, that is equal to theta. Okay, so here we will draw a construction. From point E we will draw perpendicular on BC. I will repeat again. From point E we will draw perpendicular on BC. So this angle equals to 90 degrees, and this angle will be also equal to 90 degrees according to our construction, and we will define the touching point of the perpendicular from point E and BC as F. So we actually have here the big right triangle, of course, the big right triangle, triangle ABC, but we have also here two small right triangles. The first right triangle is triangle DFE, and the second right triangle is triangle EFC. We'll define this angle as angle alpha, but in the right triangle, triangle ABC, because of the fact that this angle equals to theta, this angle must be equal to 90 degrees minus theta in order to complete the sum of the angles in triangle ABC, 280 degrees. So alpha will be equal to 90 degrees minus theta. Okay, I will write it down. Angle alpha is equals to 90 degrees minus theta. But if angle alpha equals to 90 degrees minus theta, we will add theta to this equation and we will subtract alpha, and we will get that angle theta is equals to 90 degrees minus alpha. Okay, angle theta equals to 90 degrees minus alpha. Here we have the right triangle, triangle EFC. In the right triangle EFC, this angle equals to alpha. So if this angle equals to alpha, this angle must be equal to 90 degrees minus alpha, because it completes the sum of the angles, 280 degrees. And 90 degrees minus alpha is theta. 90 degrees minus alpha is theta. We know that angle DEC, this angle equals to 90 degrees, according to what is given us in the question. So what is the size of this angle? The size of this angle must be equal to 90 degrees minus 90 degrees minus alpha, because if all the angles is equal to 90 degrees, then the size of this angle will be equal to 90 degrees minus 90 degrees minus alpha. So angle DEF will be equal to 90 degrees minus 90 degrees minus alpha. We will open the brackets here and we will get that angle DEF equals to 90 degrees minus 90 degrees, that is 0. Minus is alpha plus alpha. So angle DEF equals to alpha. Angle DEF equals to alpha. In the right triangle, triangle DEF, if this angle equals to alpha, that is to say, this angle must be equal to 90 degrees minus alpha. But 90 degrees minus alpha, 90 degrees minus alpha is theta. So we can write down that this angle equals to theta. In the next step, we will prove that the right small triangle, triangle EFC, is similar to the right big triangle, triangle ABC. So why those two triangles are similar to each other? We'll prove that they are similar to each other. We'll prove that the right big triangle, triangle ABC, is similar to the right small triangle, triangle FEC. So why those two right triangles are similar to each other? First of all, those two angles, they are equal to each other, they are both equal to 90 degrees. So angle ABC of triangle ABC is equal to angle EFC of the small triangle EFC. And both angles are equal to 90 degrees. In addition, this angle is a common angle that belongs to both triangles. It belongs to the big triangle, triangle ABC, and it is also belongs to the small triangle, triangle EFC. So we can write down that angle ACB is equal to angle ECF, and both angles, they are equal to alpha. It is the same angle that equals to itself, okay? I presented it in two different manners, but it is the same angle. So you can write down that angle alpha equals to itself. It is a common angle that belongs to both triangles. And finally, this is angle theta. Those two angles, they are equal to each other. They are both equal to theta. So you can write down that angle BAC is equal to angle FEC and they are both equal to theta. So actually prove that all the angles of triangle ABC correspondingly congruent to all the angles of triangle EFC. Those two angles are equal to each other, they are both equal to theta. Those two angles are equal to each other, they are both equal to 90 degrees. And here, this is a common angle that equal to itself. So all the angles of triangle ABC can go into all the angles of triangle EFC. Therefore, we can conclude from it that the right big triangle, triangle ABC, is similar, this is the sign of similar, to the small right triangle, triangle EFC, according to angle similarity rule. Okay? And before we will make the conclusion from the fact that those two triangles are similar to each other, we will define AE as AE equals to EC. So if AE equals to A, then EC must be also equal to A. And we will define DF as X, and we will define EF as Y. Okay? What we can derive from the fact that the right triangle ABC is similar to the right triangle EFC, we will derive that AB over AC is equal to EF over FC. I repeat again, from the fact that the right big triangle, triangle ABC is similar to the right small triangle, triangle EFC, we will derive that AB over AC equals to EF over FC. So AB over AC equals to A plus A. That is to say AC equals to 2A. And it is equal to EF equals to Y over FC equals to A. The conclusion found out that AB over 2A equals to Y over A. Here we have A on both sides of the equation, so A will get cancelled. We will multiply equation number 1 by 2, and we get that AB, according to equation number 1, AB equals to 2Y. AB equals to 2Y. Can I tell that AB equals to 2Y? Likewise, we will prove that the right small triangle, triangle EDF, is similar to the right big triangle, triangle ABC. So why those two right triangles are similar to each other? So write it down. We will prove that the right big triangle, triangle ABC, is similar to the right small triangle, triangle EDF. So why those two right triangles are similar to each other? First of all, those two angles are equal to each other, they are both equal to 90 degrees. So angle ABC is equal to angle EFD, and both angles are equal to 90 degrees. They are right angles. In addition, those two angles are equal to each other, they are both equal to alpha. So angle ACB in triangle ABC is equal to angle FED, this angle, and both angles are equal to alpha. And finally, those two angles, they are equal to each other, they are both equal to theta. So angle FDE, angle BAC in triangle ABC, angle BAC is equal to angle FDE and both angles are equal to theta. So actually prove that all three angles in triangle ABC can go into all three angles in triangle EFD. Those two angles are both equal to theta, those two angles are both equal to alpha, and those two angles are both equal to 90 degrees. Therefore, triangle ABC can go into triangle EDF according to angle similarity rule. I'll write it down. Triangle ABC is similar to triangle EDF according to angle similarity rule. And from the fact that those two right triangles are similar to each other, hence we will conclude that AB over BC in triangle ABC, AB over BC in triangle ABC is equal to DF over FA. Okay, AB over BC in triangle ABC equals to DF over FE in triangle DFE. AB is equal to 2y, we'll substitute AB by 2y. BC is equal to 6 according to what is given us in the question. DF is equal to x according to our definition. And FE is equal to y for our definition. Here we will divide both the numerator and the denominator on this side of equation number 2 by 2. So it is y over 3 that is equal to y over 3 that is equal to x times y. We'll cross multiply this equation number 2, and we'll get that according to equation number 2, y squared equals to 3x. Y squared is equal to 3x, but according to equation number 1, we have already found out that here y squared equals to 3x, but actually we can create a third equation. According to the third equation, in the right triangle DFE, in the right triangle DFE, by Pythagoras theorem, in the right triangle DFE by Pythagoras theorem, we will get that x squared plus y squared equals to 2 squared. X squared plus y squared equals to 2 squared, that is 4. So according to equation number 3, we found out that x squared plus y squared equals to 4. Here we will substitute y squared in equation number 3 by 3x, because y squared equals to 3x according to equation number 2. And we get that according to equation number 3, x squared plus y squared, that is 3x, equals to 4. So we have here a quadratic equation, and according to equation number 3, x squared plus 3x minus 4 is equal to 0. The general formula for quadratic equation is ax squared plus bx plus c is equal to 0. Here a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we will find out the value of x according to the following formula. X is equal to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, the coefficients are as follows. A is equal to 1, the coefficient b is equal to 3, and the coefficient c is equal to minus 4. And the variable that we are looking for is x, so x equals to x. So x equals to minus b, b is 3, so minus b is minus 3, plus minus square root of b squared. B is 3, so b squared is 3 squared, that is 9, minus 4 times a is 1, times c, that is minus 4, over 2a. A is 1, so 2 times 1 is 2. So we found out that x is equal to minus 3 plus minus 4 times minus 4 is plus 16, and 16 plus 9 is 25, and the square root of 25 is 5 over 2. So here we have two solutions that are possible for x. The first solution, x1, it is equal to minus 3 minus 5 over 2, minus 3 minus 5 is minus 8, minus 8 over 2 is minus 4. So we found out that x1 equals to minus 4. x1 equals to minus 4. But here you can see that x is the length of side DF of the right triangle EFD. And x as a length, it must be a positive number. So x is a length, therefore it must be a positive number. Therefore x1 that is equal to minus 4 that is a negative number is the correct answer. We'll cancel this solution and we left only with the solution that x2 equals to minus 3 plus 5 over 2. Minus 3 plus 5 is 2, 2 over 2 is 1. So we found out that x equals to 1. In the next step, I will draw the right triangle DFE, and we will implement the Pythagoras, we will do cosine theta of this right triangle. So we have the right triangle FED. This is angle theta that we are looking for. We have already found out that x is equal to 1 and DE is equal to 2 according to what is given us in the question. So here in the right triangle DEF, cosine theta equals to DF over DE. DF is 1, DE is 2. So we found out that cosine theta equals to 1 over 2. If cosine theta equals to 1 over 2, then theta itself will be equal to 60 degrees. So I found out that theta equals to 60 degrees. That is the answer to the question. Okay, the answer to the question is that theta is equal to 60 degrees. This is the angle that we are looking for. This angle is equal to 60 degrees. Okay, it is equal to 60 degrees. We finished with the first method. In the next step, I will present to you how to find out the value of angle theta according to the second method. In the second method, we will define this angle as angle alpha, which we did in the first method. Here it is A. This is also A, according to what we have already done in the first method. And here, cosine alpha, in the right triangle ABC, we have the right triangle ABC. The hypotenuse is equal to A plus A, that is 2A. A plus A, ABC. This is angle alpha. So in the right triangle ABC, we will get that cosine alpha is equal to BC. BC is 6. It is given us the question that BC is 6. It is equal to BC over the hypotenuse, that is AC. So BC equals to 6 units according to what is given us in the question, and AC equals to 2A according to our definition. So in conclusion, we found out that cosine alpha equals to 6 over 2A. We divide both the numerator and the denominator of this side of this equation Number 1 by 2. 6 over 2 is 3, 2 over 2 is 1. So cosine alpha equals to 3 over a, according to equation number 1. Likewise, we will focus on the right triangle CED. On the right triangle CED, I will copy this right triangle, DEC. The right triangle DEC. This is angle alpha. DEC. So in the right triangle DEC, we get the tangent theta. This equals to 6 units. D equals to 2 units. DEC equals to A. Tangent theta in the this right triangle DEC, tangent theta equals to DE over EC. DE is 2, EC is A. So in conclusion, found out that tangent theta equals to 2 over A So this will be equation number 2. From equation number 1, we will multiply equation number 1 by A, and then we will divide it by cosine alpha, and we will get that A equals to 3 over cosine alpha. Now we can substitute A in equation number 2 by 3 over cosine alpha. Okay, we'll do it now, and we'll get that tangent theta is equal to 2 over A. And A, according to equation number 1, is 3 over cosine theta, cosine alpha. In conclusion, we found out that tangent theta, according to equation number 2, tangent theta is equal to 2 times cosine alpha over 3. Tangent alpha is sinus alpha over cosine alpha, so we'll substitute tangent alpha by sin alpha over cosine alpha, and we will get that according to equation number 2, sin alpha over cosine alpha equals to 2 times cosine alpha over 3. We will cross multiply this equation number 2, and we get that according to equation number 2, 3 times sin alpha equals to 2 times cosine square alpha. Okay, and we have the trigonometric identity that states that sine square alpha plus cosine square alpha is equal to 1. We will subtract sine square alpha from this trigonometric identity, and we will get that cosine square alpha equals to 1 minus sine square alpha. Now we can substitute cosine square alpha in equation number 2 by 1 minus sine square alpha. We'll do it now, and we'll get that according to equation number 2, 3 times sine alpha equals to 2 times 1 minus sinus square alpha, because we found out that cosine square alpha equals to 1 minus sine square alpha. So we substituted cosine square alpha by 1 minus sine square alpha. We will open the brackets here and we will get that according to equation number 2, three times sine alpha is equals 2 times 1 is 2 minus 2 times sine square alpha we will add 2 sine square alpha to this equation, equation number 2, and we get that according to equation number 2, 2 sine square alpha plus 3 sine alpha equals to 2. We'll subtract 2 from this equation, equation number 2, and we get that according to equation number 2, 2 sine square alpha plus 3 sine alpha minus 2 equals to 0. So we have here a quadratic equation. The coefficient A equals to 2, the coefficient B equals to 3, coefficient A equals to 2, the coefficient B equals to 3, and the coefficient C of this quadratic equation equals to minus 2. And in order to find out the value of sinus theta, we will use the equation for x, the special formula. X equals to minus b plus minus square root of b squared minus 4 times ac over 2a. We will put the data inside this equation. In our case, x is equal to sinus theta, to sinus alpha. So x equals to sinus alpha, so sinus alpha is equal to minus b. B is 3, so minus b is minus 3, plus minus square root of b squared. B is 3, so b squared is 3 squared, that is 9, minus 4 times a is 2, so it is minus 4 times 2 times minus 2 over 2a. A is 2, so 2a, 2 times 2 is 4. So here we get that sinus alpha is equal to minus 3 plus minus square root of minus 4 times 2 is minus 8, minus 8 times minus 2 is plus 16. 16 plus 9 is 25, and the square root of 25 is 5. So here we will have two solutions that are possible for sinus alpha. Sinus alpha equals to minus 3 plus minus the square root of 25, the square root of 25 is 5 over 2. So here we have two solutions that are possible for sinus alpha. Sinus alpha will be equal to either minus 3 minus 5 over 2, minus 3 minus 5 is minus 8, minus 8 over 2 is minus 4. So here we found out that sinus alpha, so here we have, actually it is, we have to divide it by 4. Here it is divided by 4, and here it is also divided by 4. It is divided by 4. Minus 8 over 4 is minus 2. So we found out that sinus alpha equals to minus 2, according to the first solution, minus 2. But because of the fact that the values that sinus alpha, the function sinus, can accept values that are ranging from minus 1 to plus 1 only. Okay, here I write it down. the function sinus alpha can accept values that are ranging from -1 to +1, and -2 is smaller than -1, therefore it is incorrect solution because sinus alpha can never be equal to -2. Sinus alpha can be equal to the value that is equal or smaller than -1, or that are equal to or bigger than -1, and smaller or equal to 1. And sinus alpha can never be equal to -2, so we will cancel the first solution and we'll have to live with the second solution, that sinus alpha is equal to -3 plus 5 over 2. -3 plus 5 is 2, and 2 it is divided by 4, of course. -3 plus 5 over 4. Here 2a, a is 2, so 2a is 4. So it is -3 plus 5 over 4. So -3 plus 5 is 2, and 2 over 4 is 5. So we found out that sinus alpha is equals to 1 over 2. So if sinus alpha equals to 1 over 2, it means that alpha equals to 30 degrees. Alpha equals to 30 degrees. And here we have already found out this is angle theta, of course, the angle that we are looking for. You can see from it that this angle equals to 90 degrees minus alpha, 90 degrees minus theta. If this angle equals to theta, then this angle equals to 90 degrees minus theta. Okay, so alpha equals to 90 degrees minus theta. Alpha equals to 90 degrees minus theta, or theta is equal to 90 degrees minus alpha. Theta equals to 90 degrees minus alpha, that is to say theta equals to 90 degrees minus alpha, that is 30 degrees. 90 degrees minus 30 degrees is 60 degrees. So we found out that the value of angle theta is equal to 60 degrees, according to the second method also. In the next step, I will summarize the lecture. We'll start with the first question, of course. In the first question, we are required to find out the area of the semicircle that is inscribed inside the quarter circle. We have here a quarter circle. Inside this quarter circle, we have a semicircle that is inscribed inside this quarter circle. And we want to find out the area of this quarter circle, and we actually used a couple of laws in we defined the center of the semicircle as point C, and then from point C we drew radius to the point of tendency of tangent AB with this semicircle. So the radius CD is drawn to the point of tendency, that is to say it is drawn to point D, that is the point of tendency of tangent AB with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to this radius. That is to say, AB will be perpendicular to DC. That is to say, this angle equals to 90 degrees and this angle also equals to 90 degrees. Likewise, from the center of the semicircle from point C, we draw perpendicular, we draw the radius to the point of tendency, that is to say, to point H, that is the point of tendency of tangent VE with this semicircle, and so we have the radius CH that is drawn to the point of tendency. Therefore, the tangent BE will be perpendicular to the radius HC. That is to say, this angle will be equal to 90 degrees and this angle will be equal to 90 degrees also. And we have, because of the fact that ABE is a quarter circle, then this angle BDBH must be equal to 90 degrees. So we have here quadrilateral with 3 right angles. 1, 2, 3. Okay, and we know that the sum of 3 right angles is 270 degrees plus the size of the fourth angle must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. We subtracted 270 degrees from this equation and we got that the missing angle DCH, this angle equals to 360 degrees minus 270 degrees, that is 90 degrees. Actually, we found out that inside quadrilateral DCBH we have 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle. So in this, and we know that the opposite sides, so therefore quadrilateral DCBH is a rectangle. Okay, and we know that the opposite sides of a rectangle are equal to each other. That is to say, DC must be equal to BH. Okay, in rectangle DCBH, DC must be equal to BH. DC must be equal to BH. But DC equals to R. It is the radius of the semicircle. Okay, DC equals to R. So from this equation, R equals to DC equals to BH, we derive that BH is also equals to R. Okay, here BH is also equals to R. Likewise, CH must be equal to DB according to the rule that the opposite sides of a rectangle are equal to each other. CH must be equal to DB, but CH is equal to the radius of the semicircle, it is equal to R. And from this equation, R equals to CH equals to DB, we will derive that DB is also equals to R. DB is also equals to R, so we actually found out that quadrilateral DCBH is not a rectangle, but it is a square. Quadrilateral DCBH is a square. Okay? Then we drew the perpendicular BC of this square. We do the perpendicular BC of square BC DCBH, and in order to find out the size of the diagonal of this square, we implemented the Pythagoras theorem on the right triangle BHC. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, BH square plus HC square must be equal to BC square. BH square plus HC square must be equal to BC square. BH is R, so BH square is R square. HC is R, so HC square is R square. And it must be equal to BC square. BC is the diagonal, is the missing variable. So we got that R square plus R square equals to B square. That is to say 2R square equals to B square. 2R square equals to BC square. We took out of this equation and found out that BC equals to the square root of 2 times R. So we found out that the diagonal of this square, BC, it is equal to square root of 2 times R. Okay? Then we extended the diagonal BC until it touches the circle at point S. What is the size of line segment CS. CS is equals to the radius of the quarter circle that is free minus the length of the diagonal BC that is square root of 2R. That is to say, CS equals to the radius that is free minus the diagonal BC that is square root of 2R, or it is equal to 3 minus square root of 2R. This is the length of line segment CS. Then we completed the quarter circle to a circle, and we extended the diagonal CB until it touches the circle at this point, point M. Then I presented to you a new rule. Actually, when two chords intersect with each other inside a circle, like in this drawing, chord AB intersects with chord CD at point O. Point O is the intersection point between those two chords. Then the following formula is true, that AO over OB equals to CO over OD. Okay? AO over OB equals to CO over OD. We can implement this rule in our drawing, because in our drawing we have chord MS and chord GF. Chord MS intersects with chord GF at point C. Point C is the intersection point of chord MS with chord GF. And according to the rule that I mentioned, MC times CS must be equal to GC times CE. Okay? MC times CS must be equal to GC times CF. Okay? MC times CS must be equal to GC times CF. According to the rule that I mentioned, MC equals to 3 plus square root of 2R. CS equals to 3 minus square root of 2R. GC equals to R, and CF equals to R. So in conclusion, we found out that 3 times square root of 2R times 3 times minus square root of 2R equals to R squared. 3 plus square root of 2R times 3 minus square root of 2R, according to the algebraic identity that A plus B times A minus B equals to A squared minus B squared. Here A is 3 and B is square root of 2R. So A squared is 3 squared, that is 9. B squared is square root of 2R. So square root of 2R squared is B squared. Square root of 2 is 2, and square root and R times, and you also have to square R. So square root of 2R squared is 2R squared, and A squared minus B squared is 9 minus 2R squared, and it is equal to R times R, that is R squared. So we found out that 9 minus 2R squared equals to R squared. We added 2R squared to this equation and found out that 9 equals to 2R squared plus R squared is 3R squared. We divided this equation by 3 and we got that R squared equals to 9 over 3, that is 3. So R squared equals to 3, and the area of the semicircle is equal to the area of the circle, that is 2. The area of the circle is pi R squared. Therefore, the area of the semicircle will be equal to pi R squared over 2, because it is half of the circle in its area. So it is pi R squared over 2. Pi and R squared is 3, so we'll substitute R squared by 3, and then we divide it by 2, and we'll get that the area of the semicircle equals to 3 pi over 2 square units. The area of the semicircle is equal to 3 pi over 2 square units. We finished with the first method. Then I presented to you how to find out the area of the semicircle that is inscribed inside a quarter circle according to the second method. In the second method, In the second method, we actually relied on rule number 1 that says that a median to the base in an isosceles triangle is perpendicular to the base. Here, actually, we have already found out in the first method that quadrilateral BCDE is a square. This is a square, and the diagonal of this square CE equals to square root of 2 times R, and R is the radius of the semicircle. FC is the radius of the semicircle, CG is also the radius of the semicircle, and then from point, we joined points F and E together by a straight line. What is FE? FE is the radius of the quarter circle, that is 3 units. It is given us that the radius of the semicircle, the radius of the quarter circle is equal to 3 units. Okay? And because of the fact that EF is the radius of the quarter circle, it is equal to 3 units. Then we joined points G and E together by a straight line. EG is also the radius of the quarter circle, that is to say it is also equal to 3 units. So actually the green triangle is an isosceles triangle. Why? Because EF equals to EG. There's two sides that are equal to each other. And the base of this isosceles green triangle is FG. And EC is the median to the base FG. The median to the base, you know that it bisects the base. That is to say FC equals to CG, and it is equal to R. But it is not only bisects the base, according to rule number 1, it is also perpendicular to the base. So EC is perpendicular to FG, that is to say this angle equals to 90 degrees, angle ECF equals to 90 degrees, and angle ECG is also equals to 90 degrees. So we created here, from the isosceles triangle EFG, we created two right triangles. We divided the isosceles triangle into two right triangles. Triangle ECF is a right triangle. Okay, so we can implement the Pythagoras theorem on the right triangle, triangle ECF. Okay, here we have a triangle ECF. We know that the hypotenuse FE equals to 3 units. Angle ECF equals to 90 degrees according to the rule number 1 that the median to the base in an isosceles triangle is perpendicular to the base. Okay, therefore it is equal to 90 degrees, this angle. We have already found out that CE, it is the diagonal of the square that is square root of 2R in its length. And we have already found out that FC is the radius of the semicircle that is equal to R. So we will implement the Pythagoras theorem on the right triangle, triangle ECF. And according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. This is to say, FE square equals to FC square plus CE square. FE is 3, so FE square is 3 squared, that is 9. FC is R, so FC square is R squared, and EC is square root of 2R, so E square is square root of 2R square. Square root of 2R square is square root of 2 square is 2, and R squared, so it is in conclusion 2 times R squared. So we found out that 9 equals to R squared plus 2R squared, that is to say 9 equals to 3R squared. We divided this equation by 3 and we got that R squared equals to 9 over 3, that is 3. So if R squared equals to 3, then the area of the semicircle is half the area of the circle, that is to say it is equal to pi R squared over 2. Pi R squared over 2 is pi times R squared, that is 3 over 2. So in conclusion, we found out that the area of the semicircle equals to 3 pi over 2 square units. We finished with the first question. In the next step, I will present to you two methods to find out the side of angle theta. In the right triangle, triangle ABC, we have this angle that is equal to theta, and we want to find out the size of this angle, angle theta. We know that angle ABC equals to 90 degrees. We also know that DE, side DE equals to 2 units, and we also know that side DE is perpendicular to AC, that is to say this angle equals to 90 degrees, and this angle is also equals to 90 degrees. Okay, and we know that AE equals to EC, and we want to find out the value of this angle, angle theta. So we define this angle as angle alpha. So if this angle equals to theta, then this angle must be equal, in this right triangle, this angle must be equal to 90 degrees minus theta. Okay, so this angle equals to 90 degrees minus theta, and according to our definition, it is equal to alpha. Therefore, alpha must be equal to 90 degrees minus theta, because this angle is equal to 90 degrees minus theta also. So we found out that alpha equals to 90 degrees minus theta. Okay, alpha equals to 90 degrees minus theta. If we add to this equation theta and subtract alpha, we get that theta is equal to 90 degrees minus alpha. Okay, then we have angle DEF. What is the value of this angle, angle DEF? We know that angle DEC is equal to 90 degrees. So the value of angle DEF will be equal to 90 degrees minus the value of this angle, that is 90 degrees minus alpha, 90 degrees minus alpha. Okay, DEF equals to 90 degrees, because angle DEC is 90 degrees, and 90 degrees minus this angle that is 90 degrees minus alpha will be equal to this angle, angle DEF. Okay, 90 degrees minus 90 degrees minus alpha equals to angle DEF. We open the brackets here, and we got that 90 degrees minus 90 degrees is 0. That is to say, the missing angle, angle DEF, equals to alpha. So if this angle equals to alpha in the right triangle EFD, then this angle must be equal to 90 degrees minus alpha. But 90 degrees minus alpha is theta, so this angle equals to theta. 90 degrees minus alpha equals to theta. Actually, what we did here in the first method is that we made a construction from point E. We do perpendicular on BC. So this angle equals to 90 degrees and this angle equals to 90 degrees. Then we defined side DF as X and side EF as Y. We defined AE as A and EC is also as A, because they are equal to each other. Okay, then we proved that the right triangle, triangle EFC, is similar to the right big triangle, triangle ABC. Why those two right triangles are similar to each other? First of all, those two angles are equal to each other, they are both right angles. And then we have also this angle, this is a common angle, it belongs to both angles. Therefore we can say that this angle equals to itself. And finally, we also know that those two angles, they are also equal to each other, they are both equal to theta. Therefore we prove that all three angles in triangle ABC can go into all three angles in triangle EFC. Those two angles, they are both equal to theta, those two angles, they are both equal to 90 degrees, and this angle equals to itself. It is a common angle. So we prove that all the angles in triangle ABC can go into all the angles in triangle EFC. Therefore, triangle ABC is similar to triangle EFC according to angle similarity rule. And from the fact that those two triangles are similar to each other, we will conclude that AB over AC is equal to EF over FC. Again, AB over AC equals to EF over AC. Okay? AB over AC equals to EF over FC. AB is AB. AC is equals to A plus A, that is to say AC equals to 2A. EF equals to Y according to our definition. And FC equals to A, according to our definition also. So in conclusion, we found out that according to equation number 1, AB over 2A equals to Y over A. We have A on both sides of the equation, so A will get cancelled. Then we multiply the equation number 1 by 2, and we got that AB equals to 2Y. So here we can write down that AB equals to 2Y. Likewise, we proved that the big right triangle, triangle ABC, is similar to the small right triangle, triangle EFD. The big triangle ABC is similar to the small right triangle, this right triangle EFD. Why those two right triangles are similar to each other? First of all, those two angles are equal to each other, they are both equal to 90 degrees. Second, those two angles, they are equal to each other, they are both equal to alpha. And finally, those two angles, they are equal to each other, they are both equal to theta. So we prove that all the angles of triangle ABC can go into all the angles of this triangle, triangle EDF. Those two angles, they are both equal to theta, they are equal to each other. Those two angles, they are right angles, they are equal to each other. And those two angles, they are equal to each other, and they are both equal to alpha. So all the angles of triangle ABC can go into all the angles of triangle EDF. Therefore, we proved that the right triangle ABC is similar to the right triangle EDF according to angle similarity rule. And from the fact that those two triangles are similar to each other, we will conclude that AB over BC equals to DF over EF. We will repeat again. From the fact that the two triangles are similar to each other, we will conclude that AB over BC equals to DF over FE. AB is 2Y, BC is 6, DF is X, and FE is Y. So in conclusion, we found that 2Y over 6 equals to X over Y. We divided both the numerator and the denominator of this side of the equation by 2, and we got that Y over 3 equals to X over Y. We cross multiplied this equation, equation number 2, and we found out that Y squared equals to 3X. So then we created equation number 3. In this right triangle, you can see that x squared plus y squared equals to 2 squared. Here, x squared plus y squared equals to 2 squared. Okay? X squared plus y squared equals to 4. Here we found out, according to equation number 2, that y squared equals to 3x. That is to say, we can substitute y squared in equation number 3 by 3x. We did it and we got that x squared plus y squared, that is 3x, equals to 4. So we got here a quadratic equation, and the quadratic equation is x squared plus 3x minus 4 equals to 0, and the general formula for quadratic equation is ax squared plus bx plus c equals to 0. Here, a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula, that x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, a is equal to 1, b equals to 3, and c equals to minus 4. So we put the data, and the variable that we are looking for is x, of course. So we put the data inside the formula for x in order to find out the value of x. X equals to minus b, b is 3, so minus b is minus 3, plus minus square root of b squared. B is 3, so b squared is 3 squared, that is 9. Minus 4 times a is 1, c is minus 4. Minus 4 over 2a. 2 times a, that is 1, is 2. Minus 4 times minus 4 is plus 16. Plus 16 16 plus 9 is 25, and the square root of 25 is 5. So in conclusion, we found out that x equals to minus 3 plus minus 5 over 2. So here we have two solutions that are possible for x. The first solution for x is x equals to minus 3 minus 5 over 2. Minus 3 minus 5 is minus 8. Minus 8 over 2 is minus 4. Okay, the first solution is x1 equals to minus 4. But because of the fact that x is a length, it is length of side DF in the right triangle DEF, it must be a positive number. Here, x is length, it must be a positive number, so it cannot be equal to a negative number, so we cancel this solution. And we left only with the solution that x2 equals to minus 3 plus 5 over 2. Minus 3 plus 5 is 2. And 2 over 2 is 1. So we found out that x equals to 1. Then I drew the triangle EDF in this new page and implemented the Pythagoras theorem on the right triangle, triangle EDF. This area is also equals to, of course, equals to 90 degrees, exactly like in the original drawing. It is equal to 90 degrees. So here, according to the Pythagoras theorem, no Pythagoras theorem, but here, in this right triangle, triangle EDF, we know that cosine theta equals to df over ed. Cosine theta equals to df over ed. df equals to 1, ed equals to 2. So, in conclusion, we found out that cosine theta in this right triangle EDF equals to 1 over 2. And if cosine theta equals to 1 over 2, the angle theta itself will be equal to 60 degrees. So we found out that the angle theta, the angle that we are looking for, it is equal to 60 degrees. That is the answer to the question. In the next step, I will present to you how to find out the value of angle theta according to the second method. In the second method, we didn't do any construction, but here we defined this angle as alpha, and here this is the missing angle, so theta, cos, and as we did in the first method, this is A, and here in the right triangle, triangle ABC, we know that AC equals to A plus A, that is 2A. It is given us that BC, in the question, that BC equals to 6 units. Triangle ABC is a right triangle, it is also given us in the question. So in this right triangle ABC, we know that cosine alpha, we defined angle ACB as alpha. So cosine alpha will be equal to BC over AC. Cosine alpha in this right triangle equals to BC over AC. BC equals to 6 units and AC equals to 2A. Here we divided both the numerator and the denominator by 2. 6 over 2 is 3 and 2A over 2 is A. So in conclusion, we found out that cosine alpha, according to equation number 1, equals to 3 over A. Then we multiplied this equation number 1 by A, and then we divided it by cosine alpha. We divided it by cosine alpha, and we found out that A equals to 3 over cosine alpha. Then we focused on the right triangle, triangle DEC. We focused on this right triangle. I copied this right triangle here. Here we know that EC equals to A and DE equals to 2. And DC equals to 6 units, it is given us in the question. So here, in the right triangle, triangle DEC, it is very easy to see that tangent alpha equals to DE over EC. Tangent alpha equals to DE over EC. DE equals to 2 and EC equals to 6. DE, again, DE equals to 2 and EC equals to A. So in conclusion, we found out that tangent alpha equals to 2 over a. Okay, tangent alpha equals to 2 over a. Now we can substitute a in equation number 2 by 3 over cosine alpha, because according to equation number 1, a equals to 3 over cosine alpha. We did it and we got the tangent alpha equals to 2 and a according to equation number 1 and 3 over cosine alpha. So in conclusion, we found out that according to equation number 2, tangent alpha equals to 2 cosine alpha over 3. We know that tangent alpha equals to sinus alpha over cosine alpha. So we substitute tangent alpha by sinus alpha over cosine alpha. Okay? And found out that according to equation number 2, sinus alpha over cosine alpha equals to 2 cosine alpha over 3. Because multiply this equation number 2, and we got that 3 times sinus alpha equals to 2 times cosine square alpha. We have the trigonometric identity that sine square alpha plus cosine square alpha equals to 1. We subtracted sine square alpha from this trigonometric identity and found out that cosine square alpha equals to 1 minus sine square alpha. So we can substitute cosine square alpha in equation number 2 by 1 minus sine square alpha. We did it and we got that 3 sine alpha equals to 2 times cosine square alpha equals to 1 minus sine square alpha. So we substituted cosine square alpha by 1 minus sine square alpha. We got this equation. So we got that 3 sine alpha. We open the brackets here. 2 times 1 is 2. And 2 times minus sine square alpha equals to minus 2 sine square alpha. And we added 2 sine square alpha to this equation and we found out that 2 sine square alpha plus 3 sine square alpha equals to 2. We subtracted 2 from this equation and we got the quadratic equation that 2 sine square alpha plus 3 sine alpha minus 2 equals to 0. In this quadratic equation, the coefficient a equals to 2, the coefficient b equals to 3, and the coefficient c equals to minus 2. And we will use the formula for x in order to find out the value of sine alpha, because in this case x is equal to sine alpha. So we find out that x that is equal to sine alpha equals to minus b equals to 3, so minus b is minus 3 plus minus b squared. B is 3, so b squared is 3 squared, that is 9. Minus 4 times a is 2. Minus 4 times 2 times c is minus 2 over 2a. A is 2, so 2a is 2 times 2, that is 4. So inside this, the root we have minus 4 times 2 is minus 8. Minus 8 times minus 2 is plus 16. 16 plus 9 is 25. So in conclusion, we found out that sinus alpha equals to minus 3 plus minus square root of 25 over 4. The square root of 25 is 5. So we found out that sinus alpha equals to minus 3 plus minus 5 over 4. So here we will have two solutions that are possible for sinus alpha. The first solution is sinus alpha equals to minus 3 minus 5 over 4. Minus 3 minus 5 is minus 8. Minus 8 over 4 is minus 2. So we found out that sinus alpha equals to minus 2. But because of the fact that the values that sinus alpha, the function sinus, can accept is ranging between minus 1 to plus 1, and minus 2 exceed this range, therefore, that is to say, sinus alpha can never be equal to minus 2. Therefore, this solution is incorrect solution. We cancel the solution and we will left only with the solution that sinus alpha equals to minus 3 plus 5 over 4. Minus 3 plus 5 is 2. 2 over 4 is 1 over 2. So we found out that sinus alpha equals to 1 over 2. If sinus alpha equals to 1 over 2, it means that alpha itself equals to 30 degrees. But we have already found out that alpha equals to 90 degrees minus theta. That is to say, theta equals to 90 degrees minus alpha. That is to say, theta equals to 90 degrees minus alpha, that is 30 degrees. 90 degrees minus 30 degrees, it is 60 degrees. So we found out that the angle that we are looking for, angle theta, it is equal to 60 degrees. And that is the answer to the question according to the second method. Okay, thank you very much.